Welcome back to another lesson. Lately, we have been talking quite a bit about exponential functions. Today, we are going to introduce the inverse function of an exponential function. Before we begin, here's a quick refresher on inverse functions in general. Let's look at this example for the function f of x equals x cubed. The inverse of that is the cubic root of x. So f inverse of x is equal to the cubic root of x. It turns out that the cubic root of x, quantity cubed, is equal to x, as seen on the top line of the right side of this screen. But if you take the cubic root of x cubed, you also get x. So it seems the order in which you evaluate f or f inverse doesn't matter. You still get x either way. With a few technicalities, this is true of inverse functions in general. Let's look at this graph of y equals x squared, as seen by the blue curve. The inverse function of that is y equals the square root of x, or x to the 1/2. This is seen by the orange curve. Graphically, the inverse function is a mirror image of the original function reflected about the line y equals x. Can you see the symmetry here? To find the inverse function from a table of values, it is a simple matter of switching the columns for x and y. That is seen here for y equals x squared and y equals the square root of x. On a graph, that looks like this. Notice that the data points on the left are clustered closely together. The data points on the right are spaced further apart. What if I wanted to plot the graph with evenly spaced data points instead? That changes a few things, as we will see shortly. Looking at the data table for even spacing, it appears that now the only two matching points are the left and right endpoints of the curve. These are boxed in red and blue. Since we changed the spacing in between, we can no longer simply switch the x and y columns. Fortunately, we know algorithms to find the square root of x. We can use Newton's method or some other approach to compute the values boxed in orange. We got lucky with this function because it is relatively straightforward. In general, it is sometimes very difficult to find the inverse of a function. Now let's bring our discussion back to exponential functions. We have seen various ways to evaluate them, the favored way being a series expansion. What is the inverse of an exponential function? The inverse of an exponential function is called a logarithm. In this example, I've chosen a base b equal to 2. So f of x equals 2 to the x. The inverse of that is the base 2 logarithm. We'd say f inverse of x equals log base 2 of x. This is seen in the last line. By definition of inverse functions, 2 to the base 2 logarithm of x equals x. This is seen in the top line on the right. In the next line, we see that the base 2 logarithm of 2 to the x also equals x. Once again, the order in which we evaluate the function and its inverse doesn't matter. We get the same answer either way. Graphically, that looks like this. 2 to the x is seen in blue. Its inverse, the base 2 logarithm, is seen in orange. Notice the mirror symmetry about the line y equals x. One curve is a reflection of the other. I failed to highlight this in the lesson on graphing exponential functions, so I will mention it here. Unless we translate it downward, the exponential function never crosses below the x-axis. It has a horizontal asymptote there. Likewise, the untransformed logarithm never crosses the y-axis. It has a vertical asymptote there. That means we cannot take the logarithm of a negative number. Go ahead and try it out on your calculator. You will get an error message. Once more, given a table of data, it is a simple matter to find the inverse. Simply swap out the columns for x and y. That is seen here in red and blue. The plot of that data is shown here. Notice again that the data points on the left are clustered together very closely, and the ones on the right are spaced far apart. What if I wanted to know the value of the logarithm at x equals 20? The values for x equals 16 and x equals 32 are known. You could interpolate to find an approximation to that value. Can you think of any other approaches? What about a root finding algorithm on 2 to the x? In a future lesson, we will see a way to find the logarithm of any value x. We could use such an approach to make a plot of more evenly spaced data, as seen here. Notice the numbers boxed in red. For those integer values, it is easy to find the inverse, but for other values between them, it is not so straightforward. Look at the numbers boxed in orange. Notice they are not integer values. Here I have rounded them to 6 digits past the decimal. How did I obtain them? Well, as I just mentioned, that will have to wait for a future lesson. Go ahead with interpolation or root finding to see how close your answers get to mine. Let us know in the comments section below if you were successful. We've seen enough with base 2. The same idea can be applied to other bases. Here's a list of exponentials and logarithms side by side. I've restricted these examples to integer bases and integer exponents. I hope the color coordination helps you see the pattern. Look at the first row. By repeated multiplication, we know that 2 to the 10th power equals 1024. Now the inverse in the right column. The base 2 logarithm of 1024 is equal to 10. Same idea for every other row. Pause the video to go through them one by one until you thoroughly understand the concept. Before concluding, let's just note a few more things. We have established that the inverse of b to the x is the base b logarithm. We have seen e in previous lessons. It is so important to mathematics that we have given it special notation. The inverse of e to the x is called the natural logarithm, as seen in red. That is the meaning of ln. Lastly, it is common for a logarithm with unspecified base b to represent the base 10 logarithm. This is seen boxed in blue in the last line. Take a look at this scientific calculator. In red, I have boxed the button for the natural logarithm, and in blue is the base 10 logarithm. Notice the inverse functions e to the x and 10 to the x above them. I'd say that's enough for now. We shall continue our studies of logarithms in the next lesson. Thanks for watching.